Okay, so I'll first, so today we will do applications. So first one comment, so in the statement of arithmetic large sieve, so we had, what was it? Summation Fn square was less than n plus q square by hq into norm f square, right? So here what is n? So here n is the length of the support. Support of f. So you can take max of s minus minimum of s, where s was s a p naught omega. Okay, and f was supported on s. So f is supported on s. So because we had Montgomery's lemma and then we are summing over Q and we are applying the large sieve inequality. So the length of the sequence will come and that is n. So that's one clarification. And now we will prove a large sieve for primes. You see in the statement for the large sieve, what is the statement? You have q up to q, a mod q star, no, it's not here, a n e of na by q. So let's say m to n plus n, and this was q square plus n minus 1 into norm a square. So this is the large sieve. So this is the large sieve. The large sieve inequality. See, the problem with this inequality is that suppose n is a very sparse set, that doesn't reflect in the right hand side. The right hand side depends only on q square, this size of q and size of the length. So for example, suppose an is supported only on primes, that won't be reflected here. So what we are going to do today is something that will give a little saving, something like log n when your sequence is supported on primes. So the proposition, so let n be bigger than 2, a subset of P, which is the set of primes. So I should write it here. So this is the large sieve for primes, this proposition. And no, this is, sorry, this is not, this is P intersection 1 to n, where P is the set of primes. Then for q up to square root n, we have 1 up to capital Q, a mod q, a hat a by q square is bounded by 96 e power gamma log 2q divided by log n times n times a, size of a. So what is a hat? So where a hat of t means the indicator function of a hat of t. So this, recall, this just means E of nt, n belongs to a. So this sequence is just 1, 1, 1, but supported on a subset of the primes. And so what is the point of the proposition? So let's make a remark. If we apply large sieve, we apply the usual large sieve, we get, so ignoring the fact that this is supported on primes, etc., just apply this theorem, then q square will give you, q square is at most n, so we'll get 2n, so 2n times size of a. And instead of that, we have some constant times log q by log 2 log n. So the point is that when q is much smaller compared to n, I have a saving. So the result is non-trivial. I mean, result is new only when q is much smaller than smaller compared to n. So suppose q is like log n, then in the numerator you have log log n. So you'll have a saving of log n by log log n. And this is happening because it's supported on primes, not on integers. So it is giving you something that the usual large sieve doesn't give. And from this, the restriction theorem that Surya was mentioning today will follow. So from this proposition, the restriction theorem, which means it's an LP norm with the correct size, I mean some correct, the expected bound of the LP norm where p is between 2 and 3. Theorem of a hat, theorem for primes follow. Okay, so let's prove this result. So as we mentioned that if q is large, then this will follow from the usual large sieve. So in fact, the usual large sieve inequality implies proposition if q is greater than n to the 1/4. So assume that q is at most 1/4. Okay, and now I will decompose A. So write A as a disjoint union A naught A1, where A naught is A intersected with 1 to root n, and yes, I think that's fine. In fact, this doesn't matter. And A1 is A intersection root n to n. So then A hat of t is A0 hat of t plus A1 hat of t. And therefore, if you square it, and that is less than or equal to twice A naught hat of t square into A1 hat of t square. Now, so I can plug in, sorry? Oh, sorry. Yeah. So if I plug this in, I will have a constant 2 outside, then a0 hat plus a0 hat square plus a1 hat square. And the contribution of a0 hat square is very small. So if you just have this, and then a0 hat a by q. So here the length, so a0 hat just means sum of E na by q, and n runs over a naught. And the length of a naught is at most root n. So if you use the usual large sieve, so the length will be root n plus q square times the norm square, which is the size of a naught. And q square is at most, I have assumed q is up to n to the 1/4, so this is also root n. So this is twice root n a naught. And this is very small. This is smaller than, in fact, 16 log 2q upon log n times n a naught. So this is of the right size. This is 16 times this e to the power gamma is also there. So okay. So this is fine. This part I don't need to worry. So I have to show that this will contribute. There is a 2 also, because I will get 2, and that is the bound. So this part I don't worry with. I look at now a1 hat of t. So we need to show q up to q, a mod q, a1 hat of a by q. No, what? Yeah, that's how we wrote. Yeah, sorry, there is no square. What am I writing? That this is less than whatever we need. 96 minus 16 is, so there is a twice there. So if I divide, so 40 times e power gamma log 2q by log n times n times size of a1. If I can show this, then our proposition will be proved. Okay, and yeah, so this part is a little tricky. So let's see what we are doing. So, so define a subset of R mod Z by declaring X consists of those points X whose order in this additive group is bounded by Q. Okay. So then we can identify X with the set A by Q, where A runs from A1 to Q minus 1, A Q co-prime, and Q up to Q. Right? This set and this set are the same thing. If something has order less than or equal to capital Q, it will look like a rational with denominator up to Q, capital Q. Okay, and now I will define another subset Y by saying Y equals those elements y in R mod z whose order is at most square root n divided by q. Moreover, order of y should be coprime with R. So I have to say what R is. Oh, yeah, maybe it's better to keep it. Oh, I have already written that that's all I need to prove. So let's erase this. Where R is product over P, E up to Q, E primes. Okay, so I have two subsets of R mod Z, X and Y. Okay, and now my claim is that the map X comma Y going to X plus Y is a bijection from X Cartesian product Y to X plus Y. So X plus Y is inside R mod Z. So in particular, this would mean that all the X plus Y are distinct. And we will soon see that these points X plus Y are well separated. They are delta spaced with delta equal to 1 by n. But first, let's prove this claim. Okay, so proof. So surjectivity is clear. I mean, if it is of the form X plus Y, it must have come from some X and Y. To show injective, so suppose X plus Y equals X prime plus Y prime. Then Z equal to X minus X prime equals Y prime minus Y. Okay, and now what can you say about order of Z? So consider this expression, Z is X minus X prime. So it is like A by Q and A prime by Q prime. So then Q times Q prime will annihilate this element Z. So the product of the two orders is an upper bound of the order of the difference. So this is bounded by, this in fact divides the product of, the order will be the LCM of the two denominators, so it will divide the product of the denominators. This is order X times order X prime. Similarly, order Z is a divisor of order Y times order Y prime. But order of X times order of X prime, X and X prime both have order up to capital Q. So therefore, these are product of primes up to capital Q. Whereas orders of Y are coprime with the number R, which is the product of all primes up to capital Q. So therefore, these two are coprime. Okay, is this clear? So order of Z divides two things and they are coprime, which means order of Z has to be 1, which means Z is 0. So everything is in R mod Z. So when I write equal, this is in the group R mod Z. So up to an integer. So therefore, what we have shown is that if this happens, then essentially x and x prime differ by an integer, y and y prime differ by an integer. So that proves the claim. So I have a set of points x plus y in the circle R mod z, and now I will show that the gap between 2 points is at least 1 by n, and that's again similar kind of argument. So note that order of x plus y is bounded by order of x times order of y, right? Because it is like a by q1 plus b by q2, then its order will be LCM of q1, q2. So it's bounded by the product of the two orders. And order of x is bounded by q, and order of y is bounded by root n by q. So this is bounded by root n. So hence, the points in x plus y are delta spaced as soon as delta is smaller than 1 by root n, right? Because this means that these consist of rational numbers with denominator which are greater than root n. So if I take anything less than 1 by root n, I am fine. So we shall choose delta to be 1 by n. Okay? And with this delta, we apply the additive large sieve inequality to the set x plus y. So hence, by the additive large sieve inequality, sum over x, sum over y, a1 hat means indicator of a1 hat of x plus y square is less than or equal to 1 by delta, which is 1 by n plus n, because the length is now n minus square root n, which is bounded by n, times size of a1. So this is 2n a1, and I will call this inequality equation 1. So I will need it later, so I cannot erase this. Okay. And now we recall Montgomery's lemma. From yesterday's lecture. So in fact, I will rephrase it a little bit. So in the lemma, the set A doesn't play much role. So I will say that let F be a map from Z to C, a map with finite support S such that, okay, finite support S, and let P naught be a subset of the primes, and suppose for each prime P in P naught, there is a subset specified subset omega p, which is a proper subset of Z mod pz. Okay. So F is a map with finite support S, and I have a set of primes P naught, and for every prime P in P naught, there is a subset of this thing. Now suppose that S avoids this elements omega p when I reduce mod p. So S mod p intersection omega p should be empty for all p in P naught. So then the conclusion is, so I'll give the second version. So HQ times f hat of t whole square is less than or equal to a mod q star f hat of a by q plus t square for any q. And where I have to define what h is, where h is a multiplicative function supported on square free numbers, such that f of h of p equals omega p divided by p minus omega p for every prime p in script p naught. And omega p was the size of capital omega p. So this is the statement of Montgomery's lemma. So this earlier we wrote it a little differently. We had a set A, and we were taking a function supported on SA p omega, but this is the same statement written in a different way. Okay, so we are going to apply this lemma. So take P naught to be, so primes P up to square root n omega P to be the residue class 0. So therefore omega P is 1, and therefore HP is 1 upon P minus 1. So this is just 1 by phi of P, where phi of P is the Euler phi function. Okay, and take, so our function f is going to be indicator function of A1. So the support of this function is A1, so we need to verify that, so check that A1 mod P intersection 0 is empty, which means that the elements of A1 modulo P should not be 0, which means P should not divide the elements of A1. So this should hold for every prime P belongs to P naught. And indeed, what is A1? A1 is a subset of A, and A, we started with a subset of the primes, and A1 was between root n and n. So all the elements of A1 are prime numbers larger than square root n, and I have taken P naught to be prime smaller than root n. So obviously, a prime number is not divisible by a smaller prime number. So this condition is satisfied. So this condition is same thing as saying that P, so if M belongs to A1, then P does not divide M. And that is true for all P in P naught, because these m's are prime numbers larger than square root n. So now we can apply Montgomery's lemma, and what it tells you is the following. So instead of writing q, I will write d. So now by the above lemma, what we get is hd a1 hat x whole square is less than or equal to sum a mod d star a1 hat a by d plus x. Okay, and this is true for any d, but I will take it, I will apply it. So summing, so call it equation 2. For d, for square free d, let's say, up to root n by q, right, and d coprime with r, where recall r was the product over primes p up to root p up to q. What do we get after summing this? I get h times a1 at x whole square is less than or equal to sum over. So I have a mod d, and then d is varying over this. So these fractions a by d are precisely the set y. So I don't know if y is there or not, but we defined y to be those elements in R mod z whose orders are bounded by square root n by capital Q, and whose orders were coprime with R. And these a by d's are precisely that. That's how we have chosen this set. So this is sum over y in y and a1 at y plus x whole square, where capital H is the sum. So since I'm summing over square free, there is a mu square d, and hd is 1 by phi of d. You wrote it somewhere. Yeah, 1. So at the primes it's 1 by phi of p, it's multiplicative, so it's 1 by phi of d. And d is running up to square root n by q, and d is coprime with r. Okay. Okay, so we are almost there. So let's erase from. So now I just divide by h and sum over x. We have, you see, sum over small x in capital X is same as doing this, because capital X is precisely the set of a by q. So I can just write the left hand side. That's same as what we, that's the sum over x, a1 hat x absolute value square. That is bounded by 1 upon h, and then sum over x, sum over y, a1 hat x plus y. But this sum is taken care of by equation 1. So this is less than or equal to 1 by h to n size of A1 by equation 1. And now I need to worry about what capital H is, and that's a little technical, but it's classical number theory. So I will just quote two facts. So one, H is greater than or equal to phi r log n. So this log n saving is coming from this H. This has log n divided by 4r, and fact 2 is r upon phi r is less than or equal to 4 e to the gamma log q. And once you apply 1 and 2, so you'll get r by phi r log n, and r by phi r you bound by this. And so finally this will give you, so using 1 and 2, we get the upper bound 32. We needed 40 and we will get 32, I think. E to the power gamma log 2q by log n. See, log q and log 2q same thing. I mean, it's not a big deal. It's just to ensure that if q is 1 or something small, then it makes sense. So n times size of A1. So this is fine because we wanted to get less than 40. So this proves the proposition. So this is one application, and now since I have time, I will do the other application of Linnik. This about least quadratic non-residue. So this proof is a bit strange because we are applying this Montgomery's lemma in a situation which is not a large shift situation. Large shift situation would mean omega p is fraction of p, but still it gives a nice result. Okay, so we now start the proof of Linnik's theorem. So theorem. So let epsilon be positive, then the number of primes p up to n such that n by p, the quadratic residue symbol, is 1 for all n up to epsilon. So you see, recall that Vinogradov's conjecture says that if you go up to n to the epsilon, you must hit a non-residue. So here we are counting primes for which Vinogradov's conjecture fails. And this is bounded by a constant depending on epsilon. So the number of exceptional prime is very small. So Vinogradov's conjecture is true except for a finitely many primes. That's the message of the theorem. Okay, so proof. So the whole thing is to choose our sets cleverly. So let A be the set 1, 2, 3 up to x, where x will be chosen later. So in fact, x will be n square, but anyway. You take the set P naught to be P which are primes P up to root x, such that n by P is 1 for all n bounded by x to the epsilon. And omega P are the non-residues. So those residue classes nu mod P such that nu upon P is minus 1. So therefore, omega P is the size of omega P, and that is P minus 1 by 2. So this is a large strip situation. It is like half of the residue classes, a large proportion. Okay, and let P of M denote the largest prime factor of M. Some integer M, Pm denotes the largest prime factor. So then the main observation is the following. So integers n up to x such that Pn is less than or equal to x to the epsilon, such numbers are called x to the epsilon smooth integers. That's a subset of SA P naught omega. Okay. Is this clear why? So what is SA P naught omega? These are those integers in A, which means integers up to x, such that if you reduce modulo these kind of primes coming from P naught, it should not be a non-residue. So now if you start with the integer from here, so all the prime factors are quite small, and quadratic residue is a multiplicative function. And so modulo these primes, so suppose some r is r, let's say some number whatever, say C is here, then C by P is the product of Qi by P, where C is the product of Qi, where Qi are primes, not necessarily distinct. But all these Qi's are smaller than x to the epsilon, so they will be 1. Because if n is smaller than x to the epsilon, n by P is 1, where small p is some prime coming from P naught. So all these things are 1, so therefore C by P is also 1. And therefore it lies here, because these must consist of integers such that if you reduce modulo a prime in P naught, you should get a quadratic residue, because I am excluding the non-residues. Okay, so this is the only step that requires some thoughts. Is that clear, or should I repeat? Clear? Okay, so once you have this, so hence size of this set must be smaller than size of SA P naught omega. Now a standard fact is that this size, a set of x to the epsilon smooth integers, this is bounded above by some constants, C1 epsilon times x. So this is a standard fact. So for example, you can look at a book by Tenenbaum or any source on smooth numbers. Yeah. Yes. No, but here, see, n is a product of primes. The integer has a prime factorization. Now, all those primes are small because of this condition. And how small? Exactly is smaller than x to the epsilon. So this fact can be used. So it's a product of plus 1, so it will be plus 1. So, yeah. So this gives you, the standard fact gives you a lower bound for this. And our arithmetic large C will give you an upper bound for this thing. So let's call it equation 1. Let's call this equation 2. And I'll get an equation 3, which will be upper bound for the size of the shifted set. So by arithmetic large sieve, the size of this set is bounded by x plus q square by hq for any q. So we take capital Q to be square root x. So the upstairs will be x. And here HQ, recall, is the sum of H small q. So I won't do that. So okay, let's do that. So HQ, Q square free, Q up to Q. And that is greater than or equal to sum of HP. Q is root x, so this thing. And P has to be in P naught, otherwise it will be 0. And here, so HP is what? HP is omega P by P minus omega P. So in this case, it will be omega P is P minus 1 by 2. This is the number of non-residue. So this is P minus 1 by P plus 1. And that is always greater than or equal to 1/3. So therefore, this is greater than or equal to, yeah, P naught consists of primes up to root x. So this is just, so this condition is vacuous, it's automatically satisfied. So this is greater than 1/3 times size of P naught. Okay. So applying it here, we get an upper bound for so I have an upper bound for S, size of S, and I have a lower bound for HQ, which is 1/3 P naught. So using this, the size of S is bounded by 2x by HQ, which is 1/3 P naught, and that is just 6x by P naught. So that's equation 3, let's say. So I have, so this is smaller than this. That's an upper bound for the right hand side. This is a lower bound for the left hand side. So using equations 1, 2, and 3, what do we get? We get C1 epsilon x must be smaller than less than or equal to 6x by the size of P naught, which implies that size of P naught is less than or equal to some constant C epsilon times x. Sorry, x gets cancelled, some constant depending on epsilon. And now we choose, I think, x to be. So recall, what is the theorem? The theorem says that you should go up to n to the epsilon, and p should go up to n. So take x to be n square, and replace epsilon by 2, and that will give the theorem. Yeah. So that finishes the proof. Okay. Okay, so I think I'm done. So this is my last lecture. So after that, after this, Stefan will take over and he will talk on large Selberg Sieve.